Good morning, everyone. Welcome to the EasyPower Tuesday Refresher. For as long as the knowledge base on DC power has been around and been growing, the topic of DC arc flash is relatively behind the curve when it comes to understanding the role it plays in safety in the workplace. And especially now that we see more and more circuits requiring some element of DC content, it's a topic that there's a lot of interest in. So that's what we will address today. Again, welcome everyone. Usually we start the session with a poll question that has something to do with the either the subject matter or some of the systems. Today we're really talking more about our communications mode, so I would appreciate some feedback, if you would, on a couple items, specifically how often you find the newsletter useful, and then how often you actually access the EasyPower website. So let me, if you would please launch this poll and get some feedback on it. If you would just kind of share your comments. Nothing's binding, nothing's formal by any means, but as I mentioned in the past, we very much value your feedback, and we try as much as possible to become a source of valuable information in increasing measure. Leave this open for about 5 more seconds. Appreciate the participation. So here's how people responded to the question, and we do appreciate that. And then the second question has to do with how often you actually visit the website, and therein the direction I'm going with this is we are using the website as the basis for communicating a lot of information, and consequently we're taking steps to expand that. And so we're going to touch on that real briefly as we launch into this discussion. So again, I thank you for your participation and your feedback, and hopefully this will be all valuable information to you going forward. So let's leave this open for about 5 seconds more. We've had a very good response as far as registration for this session, and attendance is looking robust. So again, I thank you very much for participating. Here's what we're going to be talking about. I am just going to touch on some of these updates we've done to the website in case it's something you've missed. Then we will get into the basic parameters of DC arc flash. I'm not going to spend a lot of time on the difficulty involved in modeling hybrid systems, but we will touch on some of that overlap. It's an area where frequently people will come back and ask for assistance or guidance in using the tools, and it's a fun topic to touch on. So real briefly, what's happening with the website is that we are adding additional information that is relatively new, and I just wanted to show you how to access it. First of all, on the website under support, if you look at the technical support pull down, you'll see that we've expanded our hours for access to tech support. We now have people on the phones from 6:30 a.m. to 5 p.m. Pacific because we found a lot of our friends in the Eastern time zones were feeling they had to wait for a response. So I wanted to express that availability to you. Secondly, we've published a page now that's available. We're referring to as EasyPower Knowledge Base, and what this is a growing list of articles on more than just frequently asked questions. These are topics of more in-depth technical knowledge, if you will, or technical understanding of the tools. And it's very often makes sense to be able to go in and access what these articles are, and it's growing literally week to week. So I would encourage you to check if you have questions in that regard, as well as contact tech support. So anyway, I appreciate your time and attention to that. Okay, so in the subject of DC modeling, there's certain assumptions that we have to work with, and this is how the tools have been developed with these basic assertions. That the short circuit current is modeled with the steady state approximations, and we have not included any distributed inductance or capacitance, so the only contributing elements to a fault in terms of reactive fields that would collapse at a fault would be the motors. So consequently there's no inductance or reactance in the cables, and basic resistive loads don't contribute to a fault. Another modeling assumption that we utilize is fault current from a rectifier at the terminal specified is something that you have to specify in the dialog box, and we'll touch on that briefly. DC average values for both current and voltage as compared to the AC RMS values, and so there's some relationship, and based upon that we're going to share what those assumptions are. And then where we're going to spend most of our time is talking about the fact that we implement what's referred to as the maximum power method for DC arc flash calculations. So that's where we're going to be spending the next 25 or 30 minutes. The elements that we have in the tools are on the lower half or the lower portion of the equipment toolbar, which usually resides in the left vertical sidebar of the tool drawing surface. It includes DC buses, DC utilities, DC generators, batteries, photovoltaic cells, rectifiers, inverters, loads, cables, low voltage breakers, and DC fuse switches. Many of these are similar in nature and requirement as far as data as their AC counterpart, but some have specific constraints, and there's ways to interpolate the data that may not necessarily show up on a manufacturer's spec sheet. So the sources include generators, photovoltaic cells, batteries, and rectifiers, and most of these can be modeled as a Thevenin equivalent and a voltage source. The ones that are nonlinear we will touch on here briefly. And then again, DC loads really don't contribute to a short, but we do include contributions from the motors during a short circuit. Other passive devices will be the cables. Again, it's just a two-way resistance, and the length of the cable ends up being, and the dimensions of the cable end up being as important as is an AC, except for the fact that there's no capacitive or inductance as part of the equation. Converters that require attention include rectifiers and inverters, and then very much the time element that's involved in doing the arc flash calculation is going to be a factor of the protective devices, and the tools utilize the manufacturer's data sheet for fuses and thermomagnetic breakers much the same as we do in the AC side of the world. So it turns out the DC motors are, in a simplified form, have a voltage at the terminal that's equal to the voltage across the induced across the armature plus the armature current itself. So the equation for the terminal voltage ends up the induced voltage plus the armature current times the armature resistance. During a fault, that terminal voltage, fault on the terminals, that terminal voltage goes to zero, and so the impedance for the armature resistance can be calculated based upon the voltages that are left in the system, and that's the induced voltage and the resistance of the armature itself. Now, ironically, This is not something that's always been part of a manufacturer's data sheet, that being the impedance of the armature. And so we're going to touch on at least one methodology that we've used to estimate the armature resistance value, because it ends up being an important part of the short circuit model when we're doing the arc flash. And again, and more often, the data sheets of manufacturers of DC motors today frequently will include the armature resistance as part of the data sheet. So it's not that difficult on new designs or recent facility analysis. So what we've done, for example, if you don't have data sheets for older models or older motors, is to come up with some estimates. And this is essentially an example of the process we use to characterize 230 volt DC motors. First, we plotted collected data from several data sheets on a single manufacturer or manufacturers of several 230 volt DC motors at different horsepowers, and plotted the percent impedance ratio that basically was equivalent to the percent of the armature resistance compared to the overall resistance of the system at the terminal. And the plot ends up looking something like this, and this gives us the ability to come up with a value for this artificial variable we're calling percent impedance for a given size motor. So for instance, if we were going to be looking at a 20 horsepower motor, we'd expect the resistance, the impedance ratio to come in somewhere around 5 plus or minus a quarter of a percent. So you take that value and you're able to come up with an estimate of the armature resistance by essentially this equation, or the equation that we just evolved or devolved. So let's say for a 20 horsepower motor, 230 volts, and a maximum current of 83 amps, we're estimating that that's roughly a 5% impedance ratio based upon that graph that we just used. So if we apply that, or those parameters, to the equation for resistance, we take the 5% times the voltage divided by the full load current, and you put this all through a calculator and you get 0.138 ohms as the armature resistance. And that value is what we're going to use in modeling the motor when we get into EasyPower. I mentioned the battery model is a Thevenin equivalent of a voltage source and an internal resistance. Again, the resistance will vary based upon the type of battery, and here's a reference for some average values for different battery technologies. And so I'm going to run through a real quick example using a flooded lead acid battery, where we see that the impedance is roughly in the 10 to 50% range. And what we're trying to do is calculate the internal resistance of the battery. So to do that, we have a 250 volt battery. It's rated at 200 amp hours with an 8-hour discharge time. So that gives us roughly a 25 amp rate for the current. And so to calculate the resistance, we take the voltage times the per unit impedance, which is the 10% of the flooded lead acid ratio, divided by the rated amps, and from this we get a 1 ohm impedance, internal impedance for the battery. And as we noted last week, photovoltaic voltage current curves, or IV curves, have a very nonlinear plot, but they still yield some valuable information in that when we have a short circuit, the maximum current that can be produced by the photovoltaic panel or system is roughly 10 to 15% greater than the rated current of the panel. And likewise, on an open collector or open terminal basis, the maximum voltage that would be created is in the 10 to 15% range greater than the voltage rating for the panel. And again, we're going to use these later as we set up the photovoltaic components. Rectifiers in a short circuit mode at the load side can be as high, the current at the load side can be as high as the line side, depending upon the cycle that the fault happens with respect to the AC side of the circuit. So when it comes to factoring that into the contribution by rectifiers, the RMS value is probably a good approximation. Just a side note, IEEE really does not have an established standard for DC arc flash. And what I referred to as the maximum power method was first published in 2012 in the NFPA 70E, Appendix D8, and it referred to this paper that was published in a IEEE electrical safety workshop in 2007. The same model was carried into the 2015 version. For somehow it got moved up to Appendix D5, but it's still essentially the maximum power method that we're about to relay, and which is implemented in EasyPower. Now, just as you would expect, there has been continued activity in both characterizations of a DC arc and in methodology development of how to model it. So at this year's IEEE meeting, there were additional papers presented, and expectations are with the next release of NFPA 70E, we may have some new modeling made available or presented as part of that, and chances are it may come from the results from this most current electrical safety workshop that IEEE held this last month. And the advantages, because these new models, as reported, had more alignment with empirical measurements, the advantage may be the results should be less conservative than we've seen from the maximum power method. Okay, with that said, what it boils down to, the maximum power method says the arcing current is half of the bolted fall current, and so then to get the incident energy, you take 0.01 times the system voltage times that arcing current times the time of the arc divided by the working distance. With the caveat that if this arc were to happen in an enclosed box, then you multiply those results by 3. Again, the reflected energy from the 3 sides back to whatever we were looking into amplifies the energy that the worker's exposed to. So let's take all this into EasyPower and see how this applies. This is an example that's included in the sample folder of the one-lines installation of any EasyPower tool suite. And what we're looking at is a 480 volt system on the AC side that has a step down to 208, and then that voltage is rectified, and we have a DC system here that's running at 250 volts. It's worth taking a look at a couple of these elements. First of all, a fixed load basically is characterized for load flow as a constant kW, a constant current, or constant resistance, and essentially, because it doesn't contribute to the short circuit, there's virtually nothing as far as entry setup that needs to be done to characterize or prepare a load for arc flash in a DC circuit. Cables, likewise, have as we mentioned earlier, no capacitive or reactive element that's going to be utilized in the fault, there is the ability to set up the cable very much the same way as we do in our AC circuits, the exception being that the resistance showing is one way, and when we calculate that, we're actually including a double run to look at the capacity rating and the load factor. Again, has no real contribution other than just straight DC impedance in a short circuit analysis. Protective devices, again, set up similarly, and they are in the device library. You set up the manufacturer, the device breaker type and style, and then the instantaneous strip if there's a variable setting, and that will give the system a maximum time for an arc if a fault were to occur. And then more so on the motor setup, again, we're looking at making sure we have the rated voltage matching the system that we're in, the horsepower, the efficiency, and RPM are numbers that are entered but are not used in the short circuit analysis. Frequently, you need to look up the armature current, but most importantly, you need to come up with a resistance value for the armature. And this is what we came up with an estimate on, again, for a 230 volt system. And if you notice on the curve, the plot was fairly flat between 20 and 50 horsepower, so we used essentially the same resistance. Now with all that data entered, and then if we look at the rectifier, again, the voltage is pretty much what we want to be the output voltage that the rectifier is rated for, and that's going to be our bus voltage. The maximum fault current and the fault time are numbers that will come off the manufacturer's data sheet. For the most part, the diode or IGBT model is explained in the data sheet that the diode model is the simplest, and we follow that IV plot that we showed earlier. But for thyristor and IGBTs in a power flow model, there's some compromises made just because the equations themselves are fairly complex. So at that point, we have the ability to have contribution from rectifiers. We go into short circuit focus and fault the buses. And we'll see that we have on the AC side calculations pretty much that we're used to. On the DC side, we have parameters that will reflect in the arc flash spreadsheet as we've seen before. First, let's look at the fault currents. Here you can see we have 10,000 amps coming down to the DC panel where the loads are. We have 8,600 some odd over here into the motor loads. And we see a return of 1,900 or so that reduces by the time it gets to the end of the cable to 1,800 amps. So these, at least during the initial part of the fault, the motor contributions can be substantial. These factors are reported when we look at the arc flash spreadsheet, and again we see the bolted fault current, the arcing current, the bus fault current is the same as the arcing current. For the, I take that back, the bolted fault current is going to be 2x, so essentially the arcing current's half of what the bolted fault current on that bus. And then the opening time is a function of the upstream protected device, in this case BL1. When we do arc flash calculations, Those are all entered in the maximum power method, and the results are reported and will show up on the label when we print it out. So in every practical sense, the system acts very much as we would expect the AC, or we see the AC calculations to proceed. I do want to take a brief second to, for some reason this GoToMeeting session is slowing down my display. So you'll see as we, in this case we're just looking at one bus, we show our arc flash boundary, the incident energy, and then a reference to the table for PPE, 250 volts electric shock, limited approach, and then restricted approaches essentially just don't touch the DC bus. Now I did want to touch on the fact that and it's less complicated if I use elements that don't have overlap with the AC side, the hybrid side. If we go into coordination, we can plot the, in this case, these two breakers. And if we wanted to coordinate downstream protection, we'd have the ability, or the same ability, to make adjustments if we're talking about an adjustable breaker, so that we can get coordination or separation. And as with most molded case circuit breakers, you're always going to have some potential for overlap when as far as the instantaneous trip. So I guess the takeaway from this is you must, I guess, be logical in your approach to modeling elements that the manufacturer's data sheet doesn't have complete data. There are ways to come up with estimates that are close approximations in the cases of motors, and the tool pretty much takes care of the rest. So again, I invite you to play with this particular example in your sample folder. There is another example I wanted to show that these are available. If for some reason you don't have them in your installation, you're more than welcome to contact me, and we'll get you copies of the example one lines. There's another example I wanted to show that essentially is shows a bypass switch and the change in calculations as we're doing AC conversion and then bypassing that function. If we fault all the buses, we can see that the AC current from the DC bus is bypassed, and consequently the incident energy at the downstream AC bus changes based upon what that current source is. One thing that was of note as I was looking at this particular example, and I just want to fault this one bus, is it's because this is an AC bus. If you look down here at my bolted fault current, we show 180 amps as the bolted fault current, and the arcing current showing 222 amps. And a keen eye observer like Street might suggest that something fishy is going on, and he'd be right, and it turns out this is quite literally a function of the IEEE model and the nonlinearity, or conservative values that you get when you're in a low voltage side, less than 240 volts of AC calculations. So I just invite you to keep an eye out for that. For those of you that have to deal with low voltage AC calculations, again, I'd encourage you to get from the website or from tech support the application note on how to handle low voltage AC arc flash. So that pretty much covers the information I wanted to talk about today. We will answer questions here offline, and I appreciate everyone for attending, and we'll talk to you next week.